not on yet. Okay. It's on? Yeah. Okay. Thank you again, Alfonso. Yeah. So today I'm going to talk about a class of problems about finding periodical solutions of Hamiltonian systems. And the method is using variational method that has seen a great stride in the last 30, 40 years, and in particular toward applications in PDEs, ODEs, and then we have seen some nice applications from Monica's talk this morning and in PD problems. And I will speak about the ODE problem here. The topics, the topics I'm going to discuss today. So I start with the fixed point theorem, and due to Poincaré and Birkhoff, and which can be used to find the periodical solutions in lower dimensional Hamiltonian system. Lower means 1 or 2 dimension, and 1 dimension Hamiltonian or 2 dimension ODEs. And in this theorem, there is a twisting condition, and people have tried to generalize this condition to higher dimensional systems. To discuss these generalizations, we need to review an index theory and called the Conley-Zehnder index, and also involving some resonance conditions. And with this index theory and our survey, some of the past and the recent result in this line of work, and just using variational method to find the periodical solutions. So let's start with this fixed point theorem. This theorem is also called Poincaré's last geometric theorem, and was one of the last few formulated by Poincaré, and then Birkhoff gave a theorem shortly after. But this was almost 100 years ago, and around 1910. And it's a very simple theorem, and you have an annular domain in R2, and you have a map. This domain we call the R. You have a map phi, which is a homeomorphism, and is a 1-to-1 onto, and the inverse is a continuous, just a map. And it's also area preserving. Okay? So if you take a small piece area, and then under this phi, and go to another place, the area is the same. Then the key condition is this twisting. And so phi advances a point on the outer boundary one way, and then positively, for example, and then point on the inner boundary negatively. That's those arrows for, and so in this case, on the outer boundary and moving clockwise, and the inner boundary counterclockwise. A fixed point, so under these conditions, the conclusion is phi has at least 2 fixed points in this annular domain. A fixed point is a point that phi does not move, so it's a phi x equal to x. I like to give the student something they can take home, and here is a piece of that. And so let's give a sketch of the proof of this theorem. Let's take a point on the inner boundary, a point on the outer boundary called B, and this is A, and then you join these two to get a line segment. And take this line segment in the radius direction. That means when you extend it, passing through the origin. And now we claim the first observation is, so there has to be at least 1 point on this line segment. It only moves in the radius direction under this map phi. So you may think that this is in polar coordinates, you have a radius direction, angular direction. It doesn't move in the angular direction. You can see this, just think about under this phi, and this piece of line segment becomes a curve, right, in general, because of the twisting. And so on the outer boundary, it goes one way, and then on the inner boundary, it goes the other way. And so this new curve, the image of this line segment under phi has to intersect the original line segment somewhere. Then that point is the image of another point on the line segment under phi. And so that means you find at least 1 point, and that does not move in the angular direction, but only moves in the radius direction. And now let's take a curve, but you can take this line segment around this annulus, and so in every annulus, on every direction, you're going to find such at least such one point. Let's take a C to be a curve of points that only moves in the radius direction under this phi. And I call that curve C. That's a C is a curve, and it contains points that only moves in the radius direction under this map. And consider the image of this C under phi. Let's call the phi of C. It becomes a different curve. And the second observation here is any point in this intersection is a fixed point of phi. This is easy to see because any point on C doesn't move in angular direction. And then if a phi C equal to C at the point, and then that means it doesn't move in the radius direction either. So it has to be a fixed point there. And so now the final punch here is this set contains at least 2 points. This is due to the property phi is an area preserving map. And just think about the area contained by C and phi C. If these two curves intersect only at one point or have no intersections, and then the area contained by C and the 2C will be different. And so that gives you this intersection contains at least 2 points. Then you may be wondering, so this is a quick proof of this theorem. Then you may be wondering what's the relation with the differential equation. It turned out that there are a lot of maps generated from ODE that's area preserving in 2 dimensions, and then in higher dimension called the volume preserving. So let's look at this initial value problem. And so it's a first order n dimension ODE, and then let's look at this initial value problem. We assume this vector field is smooth enough, and the solution is denoted by phi sub t of y, and so in t is a solution of this equation, and then when t equals to 0 is y there. Now, for fixed t, you consider this a map from Rn into Rn, and then by ODE theory, and then you can easily see this is a homeomorphism, and then you can take phi sub minus t as its inverse map, and so you have a family of homeomorphism of from Rn into Rn there. Now the proposition, if this vector field is divergent free, so the divergence is 0 there, then for any t fixed, this is a volume preserving map. Just recall this divergence is this quantity, and so f has n component, and then you take dj's component differentiated with respect to dj's argument, dj's component of x. And but if you consider the derivative of f is an n by n matrix, and then this quantity is also the trace of the derivative matrix there. Let me give you also a sketch for this proposition. So let's take a piece of a domain called D. And then d of t is the image of d under this phi of t. And so we want to consider the volume change in terms of t. Let's call the volume of d of t to be v of t there. And then we know this phi sub t is a transformation Rn to Rn. And when you want to calculate the volume, and so you just integrate the Jacobi there. Okay. So this is the Jacobi of the transformation. Now the claim is the derivative of this quantity with respect to t is given by integration of the divergence of f. And so if the divergence of f is 0, then this derivative is always 0, and so the volume does not change. And so you get a volume preserving map there. To get this claim, and then it's because we want to compute the derivative at 0, so let's just expand this quantity v of t in t for t tend to 0. The leading term when t equals to 0 is the initial value, that's x. The first order term, you take a derivative with respect to t, that's f of x. And so then you have a high order terms there in t. And then you take, you're going to take a derivative, and so this give you identity, and the derivative of f, and again is a n by n matrix, and then we have the high order term there. The Jacobi is the determinant of this matrix, and so because we are only interested in the expansion in T as T tends to 0, let's collect the terms, and so this will be constant term coming from this identity, and the coefficient for the first order term. Imagine any interest in this f prime, if off the major diagonal involved, and it's going to appear twice, and so you're going to have a high order term. So the only terms involved for the T first order here and are those on the major diagonal there. And then you can easily check, and then the coefficient for the leading term, for the first order term, turned out to be the trace of this matrix. And then once you have this, and then you bring this back into this formula, so you have this expansion, so the derivative will be given by this term here. So that's this volume preserving maps. And among the different equations that share this property, there is a special class that's called the Hamiltonian systems. And it has this particular form. It's always an even dimensional system. And so Z is in R2n. And this H is a scalar valued function, and called the Hamiltonian function. Let's assume that's smooth enough. This J is a 2n by 2n matrix, and put into blocks like this. So you have a n by n identity with a minus, and the identity here is the standard symplectic matrix. And but you don't have to worry about this form, and you can always write in component fashion, and if you write a Z in two blocks, and so P and Q both are n vectors, then the first n equations of the system become this. So it's a Pj prime, and with this form, and then you have the last n equations of this form. But these are not so special, and many of the second order equations from mechanical systems and appear as special cases of a Hamiltonian system. And I listed a couple here, and I think everybody is familiar. The first one is the harmonic oscillator. If you take a Q double prime plus alpha square Q equal to 0, and you can write first order system. Then the Hamiltonian you can easily write in this form. The second equation is the pendulum equation. So a simple pendulum, and the Q is the angle for the pendulum. And then this can also be written in this first order system, two equations, and then the Hamiltonian is this form. So this is the total energy, in fact, for the system, and this is the kinetical energy. This is the potential energy there. Now, the first point I want to mention here is, for such a system is always a volume preserving, because you look at this formulation here. When you want to compute the divergence of the vector field on the right-hand side, you're going to take a P derivative of this and a Q derivative of this. So they both become second-order partial derivative, but a mixed P and a Q. But here there's a minus, and so when you add together, it's always 0 there. So that's the first. The divergence of this vector field is always 0, and so that means for any T fixed, the flow map generated by this system of different equations are volume preserving. Okay. In particular, in two dimension, they are area preserving. A second point here is, for any tau fixed points of phi sub tau correspond to tau periodical solutions of this Hamiltonian system. Just imagine you start from here, then by time tau, you come back, and so that's just a periodical solution. So if you find a fixed point of phi sub tau, and then you find the tau periodic solution of this system differential equation. Then let's look at a very special case, and where you can use the Poincaré-Birkhoff theorem to find periodic solutions. There should be one line above that, and then oh no, it's here. So we take a very special case, n equal to 1. That means you have a pair of equations. Let's assume this H is very special, and so Z small, it behaves just like a linear system, and is alpha is a constant times Z there. Then for Z large, and then it behaves like also like a linear system. It's a beta times Z. And in fact, they are both harmonic oscillators. And when you write this in a pair of equation, is a P prime equal to minus alpha Q, and then Q prime alpha P there. And so that reduced to this second order equation. And so now where we can find solutions in tuner. And I want to find the parameter solution in some period, let's say for community locations. So you want to find the Poincaré-Birkhoff theorem. And assume this alpha and the beta with probability of k separate numbers, say k is 0. Then this physical 2I can be regarded as moving in opposite directions. And on the circles near 0 and circles with the alpha negative, the solution near 0 rho is clockwise, and then solutions far away in terms of beta rho is counterclockwise. As a condition, twisting condition in the Poincaré-Birkhoff theorem, this 2I has 2 forces in annular which to do two solution of the music. There are two solutions in there. Doesn't matter where the lie on. Now let's consider higher dimension system. Let's take a little more general situation. So we are looking for paradox looking for solution. And this in R1. Let's assume the 1, 2 will be called the inlet. And H1 has this symmetrical expansion near 0 and the unity. And the other unity are 2 pi Brado. You find the Poincaré-Birkhoff theorem does not apply in higher dimension because that's Hamiltonian system. Let me review the real setting of the problem. And so you have this looking for the solution of the main will be a circle, and then you can start two functions. Sorry, equal functions. This is function the function and then the rhythm may be written as form. Now the first is important is important is corresponding to k as eigenvalue, and is given this form as you can get cosine kt involved there. For the nonlinear part, and so let's write this functional. We integrate this h, the Hamiltonian, so you get a functional, and it's defined on z there. Then this is a C1 functional. So the original Hamiltonian system can be written in this form as an operator equation. And then you define the so-called action functional. It contains the quadratic form involving this operator A, and then you have this nonlinear functional and G. Then this operator equation, or the Hamiltonian system, is really the Euler-Lagrange equation of this functional. Yeah. And so the problem to find a periodical solution, 2-pi periodical solutions of the Hamiltonian system now becomes to find the critical points of this functional f. To discuss about the twisting condition, we need to introduce a few things. Non-degeneracy first. This B sub t is always a 2-pi periodical continuous and symmetric matrix function here. It's called a non-degenerate or non-resonant if the linear system, this linear system, does not have a 1 as a Floquet multiplier. Or equivalently, this linear system does not admit a non-trivial 2-pi. The first result in the 1980s says you get a non-trivial 2-pi periodical solution for the harmonic system. And if a twisting type of condition is satisfied by non-degenerate infinity. To discuss this twisting condition, we need to review a little bit of the is a new map to the set, and inside a matrix that has no eigenvalue. By Kelly, Zimmer, and non-linear, this set can be done into a countable connected component. So you can attach component either and then we find the Nonlinear index for this B to be the integer that is associated to this W in that gamma. So this W is given into the connect component in that gamma, and then the index will be same integer there. For the degenerate matrix B, and then you can extend the motion. The degenerate index is going to be a pair of numbers. The first one just like this. They give my approximations through non-degenerate ones. The second number is a number either to 0 and to n. Is the measure of the kernel of this matrix is W to pi minus I. That's where W and then for h prime, but assuming not infinity both non-degenerate. And now the x and the 0 and the index infinity are different. So the twisting is reflected by this the times index is given between 0 and infinity. Let me give you a special case here. In the case if R a constant times identity, infinity is a constant times identity there. And then if assume R is a negative, is a positive, then the index near 0 is no more than minus n. And the linearity is less than. So in case this R is this will be the minus be exactly equal to 1. But here assume this degenerate. That amount to say this R is not integer. So that R integer and separated by the number 5. I view the Poincaré-Birkhoff theorem based on H actually last 20 some years and to allow B naught B infinity to be degenerate. Here I just want to mention, but in the literature there are also mainly this two type of result. One type of result is to allow this B infinity to be degenerate, but requiring some more conditions and for this Hamiltonian function. And for example, this condition in the literature called the Lanzmann laser type of condition, and this says H has this expansion at infinity, but you require the difference to be large in some way. So after integration, and for Z in the kernel of this operator, because you allow B infinity to be degenerate, so there's a non-trivial kernel here. There are also some other type of result, and for example, so-called the strong resonance condition, and that roughly says this term has to be very small, and so going to 0 in some order. There are many conditions given variations of this type, and in the literature, and the people are still working on this. And due to time constraint, I'm not going to list any specific result here. But I do want to point out there's another line of work in nonlinear elliptic boundary problems, and in this spirit, and Alfonso was one of the pioneers in 70s, late 70s, early 80s, and doing that type of work, and has inspired many work to follow there. Okay, now this is the other type, the second type of result. This type of result also allow resonance at infinity, but without requiring any additional condition, essentially. But the catch, the price they have to pay is they're going to require a stronger version of the twisting. Sorry, I forgot to say the twisting condition for the first type result is in this form, because there's a non-trivial kernel, there's a nu of B infinity there. So as long as this index at the 0 does not belong to this closed interval, and then you get a non-trivial 2 pi periodic solution. And assuming B naught is non-degenerate, there are some other results allowing B naught to be degenerate, but let's just, for now, just assume B naught is always non-degenerate.
What is mu B infinity?
This is the kernel of the dimension of the kernel of this Albert. Right, yeah. The dimension of kernel. So it's between 0 and the 2n there. In using a variational method, in particular Morse theory, it seems that this is the natural generalization of the original twisting condition. Now, the second type of result said they also allow non-degeneracy at infinity and without requiring any additional technical condition. But the price they have to pay is require a stronger version of the twisting here. So this interval is widened by 2 units, 1 unit to the left, 1 unit to the right. So this is the I of B infinity minus 1, and here is you add 1 to the right. And if the index at 0 does not belong to this interval, then you get at least 1 non-trivial 2 pi periodic solutions. And this is a concrete result, and it assumes slightly stronger than that 2, the expansion for H prime at infinity. This is rather for the H double prime expansion at infinity. Yeah. And assume B naught is non-degenerate, and then if this twisting condition is satisfied, then the Hamiltonian system has at least 1 non-trivial 2 pi periodic solutions. And this result was motivated by an early work by Benchi and Fortunato for second-order systems. There's a corresponding theory for second-order system. But then was extended later to first-order system by Pisani, who only got a partial result. Now this is a full result here. Now let me discuss recent work of myself. This is a result to drop the condition on F to have a asymptotic expansion at infinity. So instead of assuming it has a linearization at infinity, we only require the second derivative to have a kind of a comparison with another quantity there. It's a joint work with Liu and Su, both from China. So this first condition just is a smoothness condition. And then this says H prime has at most a linear growth here. The third condition is just saying 0 is a trivial solution for the Hamiltonian system. And we assume this new 0, that means B0 is non-degenerate. The key condition is this H plus minus 4 here. We assume there is a 2 pi periodic symmetric metric function called a B sub infinity, and with which is non-degenerate, such that for some k and z is larger than k, and this comparison is satisfied. And so H double prime is staying on one side of this B infinity. By the way, this is 2 matrices, and then one matrix is greater than the other one. I mean, if the difference is a positive definite in the sense. Okay? So the difference of the 2 is a positive definite matrix. And assuming this, so this is the plus minus, there's a pair of conditions. Assuming, for example, plus, then if the index at infinity is greater than the index at 0 plus 1, or in the minus case, and then if the index at B infinity is less than the index at 0 minus 1, then the Hamiltonian system has at least 1 non-trivial 2 pi periodic solution. The condition, this twisting, is more the same as the second type of result. And the difference is that we don't require the Hamiltonian function has any expansion at infinity, it only has this comparison. And so it extends the result, the last theorem I posted up there, and to a wider class of Hamiltonian systems. But then this result also allows the Hamiltonian to have interactions with as many as the eigenvalues of that linear operator as possible, and just under this linear growth, and then you may include many resonance at infinity as you like there. This the method that we use also can be extended to trade multiplicity result. I just want to put this result there, and this type of result exists in the literature for the first type of result I mentioned earlier. Okay? And so if the index at the 0 and infinity separated, and then if you assume in addition this h is an even function in Z, and then you get a multiplicity result. I just want to mention the method we use also carries to this situation, and so in case of H4 plus, and if this condition is satisfied, you get this number -1 pairs of non-trivial 2-pi periodic solutions. This is a few remarks I already just mentioned, and so it extends the second type of result, and now you allow interactions between the nonlinearity and the linear spectrum at infinity. Now let me give you an outline of the proof. The basic idea is to modify the original problem so that you can work on the modified problem, and then you can control the solution you get for the modified problem. So eventually you get solutions for the original problem. This general idea has been used by many people, but the difference here is, for example, the second type of result I mentioned there, allowing non-degeneracy at infinity without any technical conditions. They did modify the original problem, but they use a rather non-local modification. So they have this variational functional. They modified the part associated with that kernel, the function in the kernel, and so that gives you a non-local modification. And here we're going to modify the Hamiltonian functions directly. And so you're going to get a sequence of Hamiltonian, and they are non-degenerate at infinity. So you can start to work on them. But this has to be done in a careful way. We want to keep this h plus or minus intact or uniformly satisfied for this whole family of modifications. A simple cutoff, it doesn't work if you just connect this original Hamiltonian with some thing you just set up infinity. And so it's the modifications is global, and so from somewhere on has to be extended all the way to infinity. Then the second thing you need to do is, due to the indefinite nature of the problem, because the spectrum goes from negative infinity to infinity, and then we're going to make so-called a saddle point reduction. And the problems, this family of problems, will be reduced to a family of problems in some bounded, in some finite dimensional spaces. This process now is a standard, but the difference here is the dimension we're going to use for each of the problem here may be increasing. So it may not be the case you can use one reduction that will do all the work here. So a careful look here. All this careful or control for the modified problems eventually will be used in the place to get control for the solutions to the modified problem, because eventually we want to get L infinity control for the solution. And the third step is for each of the approximate problem, you use either Morse theory or minimax principle to get solutions, and whose Morse indices can be estimated from the construction here. That will be used also in the last step. So in the last step is you're going to establish the so-called L infinity bound for the solution constructed for the modified systems. And this makes use of the most indices information together with in the second part you have this increasing dimension, and that will give you some nice estimate for the approximate solution there. So this is just outline or outline of the approaches, and I couldn't get into details here. Let me just finish with a couple of further questions. The first one is a more natural twisting conditions, and the one in the last result we dropped the asymptotical expansion condition for the Hamiltonian at the expenses of requiring a stronger twisting. Remember that interval is widened by 2 units, and one to the left, one to the right. Okay? And then there should be a condition that's more natural and in the spirit of the Poincaré-Birkhoff theorem there. And the second thing is about multiplicity result without symmetry. I did mention one result that gives you multiplicity, but that makes use of the symmetry of the problem. But without any symmetry, can you get a multiplicity result? That seems a difficult question. Let me just finish here.
Questions or comments?
Okay, so in